Okay, looks like we are live here, and I'm working on section 5 of chapter 2, so section 2.5. This is day 3 of implicit differentiation. So, what do we know about implicit differentiation? Well, we've learned quite a bit so far, and now what we're going to do is take and use it in an application. And one of the new things that we click on here is what is a normal line? What's a normal line? Well, we are used to tangent lines, aren't we? Tangent lines are where we find a point and draw a line that is just adjacent to the point and skims by it. So that would be a tangent line. Now we're coming in with normal line. Definition for a normal line. Sorry about that. Didn't mean to highlight. Let's get the definition of normal line is a line that is perpendicular to the tangent line at that point of tangency. So maybe you want to hit pause so that you can write that down, but I'm going to describe what this is. We talked about this as the tangent line, didn't we? Here's my tangent line. Now we just got this definition about a normal line. It's a line that runs perpendicular to the tangent line at the point of tangent C. So here's my point of tangent C. Then this is my normal line. Notice how it runs perpendicular, right angles, to the tangent line. On this circle, looks like that would definitely go through the center of the circle, doesn't it? I think you could prove that fact. All right, so doesn't sound all that much, not that much more difficult. But what we will do is we're going to trace back and do the same steps that we usually do. Let's find the equation of the tangent line, or at least the slope of the tangent line. And if I have the slope of the tangent line, then I should be able to find the slope of my normal line, because I know how perpendicular lines intersect. Their slopes are, when multiplied, would equal 1, right? Which means that one of them is the opposite reciprocal of the other. So drawing on that old information from algebra. So we have a circle equation, x squared plus y squared equals 100. And I want to find the point of tangent C to be 6 something. If I plug in 6, let's just find y here. And this looks as good a place as any to do that. Let's find y. I'm going to plug 6 in. 6 squared plus y squared equals 100. That means that y squared is equal to 100 minus 36. Or y squared is equal to 64. Therefore, y is equal to plus or minus 8. So I have actually 2 spots here. When x is 6, I get plus and minus 8. 6, 8. Who do we appreciate? Right there's one of my points. And 6, negative 8. Where? 6, negative 8. My graph's a little bit off. I'll just make the dot bigger, right? So here's one of the points, 6, 8. And down here I have 6, negative 8. Now, what we want to do is find the derivative. And the derivative for this would look like 2x plus 2y dy dx, implicit differentiation, equals 0. Solve for dy dx, we'll have 2y dy dx is equal to negative 2x. Sliding it over to the other side, right? I subtract 2x from both sides. Boom, boom, boom. Divide by 2y. And that'll cancel on this left side, and I get the derivative dy dx is equal to, negative 2 over 2 cancels down to 1, divides into and makes 1. I get negative x over y. Let's hang on to that. So I'm going to just square that out. The tangent line at the point 6, let's just do it at 8. Okay, we'll just pick one of our spots and we'll take the quadrant 1 point, 6, 8. The tangent line, well, I know my slope, right? We can calculate our slope. We need two things to write an equation. We need a slope and we need a point. The point was given to us, 6, 8. The slope, however, I'm going to take my dy dx, evaluate it at 6, 8. Remember how we can draw this vertical line, which means evaluate, and then I'm going to tell you what I'm evaluating it at, 6, 8. Plug in, x comes first, so -6 over 8 looks like a -3/4 slope. If I take that information, the slope as well as the point, I can write my equation, y minus the y value equals the slope times x minus the x point. And there's the equation of our tangent line. If we drew it in, it would look something like that. Suppose I got a slope of up 3 over 4. I'm sorry, down 3 over 4. 1, 2, 3, 1, 2, 3. Hey, not so shabby. Down 3, right 4. I did a pretty good job. Because we know how, whoa, sorry. Was not erasing for me. Wanted to clean that up. We knew the slope should be -3/4 when we're at 6, 8, and boy, it was. Now, what we were after was the normal line, weren't we? How do we get a normal equation? Well, normal runs perpendicular to the tangent line. So I need my normal line slope is perpendicular to the tangent line slope. And I knew my tangent line slope, the tangent slope we just talked about, was -3/4. That makes then the normal slope opposite reciprocal positive 4/3. Check it out. When I multiply the two, I should get -1. Aha, we do. Awesome. All right, now all I got to do is write the normal equation, and we're grabbing the same point, 6, 8. So I take my new information and I write y minus 8 is equal to 4/3 x minus 6. Normal line. Cool. Love it. We had a picture up here. This looks like it's maybe a sphere. The surface is a sphere. And these would be all a bunch of normal lines. They're drawn perpendicular to the tangent line of that spherical surface. You know what it brings to mind? The giant dandelion. You find them out, in nature. Often you see them in roadside ditches. And they're huge. Like if you can see this kind of compared to the hand, they're pretty good size. They're quite large and rather delicate. If you tried to pick one, they kind of fluff away because that's their method of dispersion, isn't it? The wind grabs them and plants the seed somewhere else. So how do you pick them and keep that beauty? Hairspray. Hairspray them. It'll hold. Make some stick and then you can cut it and won't disperse on you. All right, higher order derivatives. What is a higher order derivative? Well, it's like when you take the second derivative or the third derivative or the fourth derivative. It's quite easy to do. Can we do it when we have implicit? Well, certainly we can. So let's find our first derivative and then we'll go into a second derivative. All right, so first derivative, I would have 6x squared minus 6y dy dx, correct, equals 0. We want to solve for dy dx. So that means I need to get the terms separated. It's -6y dy dx is equal to -6x squared. Oh, let's multiply both sides by a negative. Should have just added that other over. All right, so we got positive equals positive. Now let's simply divide by 6y, simplify, and we get dy dx is equal to x squared over y. Not bad. But our objective wasn't to just get the first derivative, it was to get to the second derivative. So now let's go into play off of the first derivative going into second derivative. So I'm going to be all about this. Ah, shucks, we got quotient rule coming our way, don't we? We will use the quotient rule. So because I'm using the dy dx, the Leibniz notation, we must, the notation looks a little different. It's a d squared y over a dx squared. And if you want to check out why that is, you could go to Wikipedia, had a pretty decent explanation of it. And check that out. I'll explain it in class otherwise. So we get the second derivative. Well, we are all about the quotient rule here, right? Quotient rule is what's happening. Derivative of the top is 2x multiplied by the bottom is a y. Subtraction is involved when you do quotient rule. Now we take the derivative of the bottom, which is a dy dx. Notice I moved it to the right because I want to fit in multiplied by the top over bottom squared y squared. Hey, not bad. What I was going off of was, some of you have these memorized, like u over v. Well, it's u prime v minus v prime u over v squared. And that's what we utilize to do our quotient rule. Now, I bet you're feeling really good. I'm going to burst your bubble a little bit because I see an issue. What's this? I'm sitting with the second derivative defined using a first derivative? There's a way to fill that in, right? I think I should get rid of the first derivative symbol in there. What can I replace it with? Well, I just so happen to know what the first derivative is. It's x squared over y. So what we'll do on these higher order derivatives is we will bring this back in and substitute it for this notation dy dx. Does that make sense? I simply replace the dy dx with what it is equivalent to, x squared over y. Now I ended up with a higher order derivative that is totally in terms of x and y. I suppose I should clean this up a bit, huh? I get 2xy minus an x to the fourth over y divided by a y squared. I still can clean this up. Let's make a denominator for this one. Okay, right now it's 1. I would love to join the top two terms together. And in order to do that, this one must have a y. So then I have to multiply by y, which will force this to a y squared. Now we've got 2xy squared minus x to the fourth over their common y. This is like y squared over 1. So multiply by its reciprocal, 1 over y squared. And we get our final answer of 2xy squared minus x to the fourth over y times y squared makes a y third. This is our second derivative. So higher order derivatives can be a little bit of work. They typically will involve replacement. We could go through this. You know what? I kind of cut us a break here, didn't I? I'm giving us what the first derivative is. So let's work off of that fact and go into a second derivative. So I want to get to my second derivative. And I could say y double prime, or I could go y dy dx. D squared y over dx squared. And quotient rule again, derivative of the top. And when I say I'm working off of that up there. So my eyes, you can't see my eyes, but they're peeled up to the right corner here. Derivative of x is 1 multiplied by the bottom. Minus derivative of the bottom, which is a dy dx, multiplied by the top, all over bottom squared. And like we predicted, and not a huge surprise, we have our second derivative written in terms of a first derivative. So we want to clean that up. So our second derivative will equal y minus x replace. So we substitute in x over y. This was over y squared. And that would equal y minus x squared over y squared. Once again, I would love to join these two together. Right now it's y over 1. We want to change it to a denominator of y. In order to do that, I got to multiply by y over y, don't I? And y times y on top makes a y squared over y. That allows me to push these two fractions on top. I can add them together and then multiply by the reciprocal of the bottom. That gives us an answer of y squared minus x squared over y cubed. And we're done. So that pretty much finishes it up. I think up to this point you should have these problems done. This was the day 2 assignment. And so now finish it up, please, by doing these last 4 as our day 3 assignment. And that concludes the section 2.5 for us. Thank you, guys.